first, in the past, you did conics in regular, normal XY coordinates, normal rectangular coordinates. Now we're going to be doing it in a polar graph, which is why I passed out a polar graph. First thing we have to look at is what eccentricity means. Eccentricity is not necessarily only someone being really strange, like all of you thought, we all thought Mr. Sharp was. You know, I wish he was still here because I had so much fun with him all the time and things like that. But you know, there's nobody else I can really say that about anymore because nobody is like Mr. Sharp. But we all know people like that. So, however, we're going to apply it here to conics. And what we're going to be looking at, I'm going to be referring to this a number of times. Oops, I like this little graph. And if you go in and look at various videos and things on the internet, they all go back to this kind of thing, where you will compare certain things here. Like on this one, we have here, okay, we have from the focus point to a point, any point here, gives you a certain amount of a line. And then from that point over to the directrix to make a right angle is a certain distance. So that distance of P to F divided by P to D gives you the eccentricity. So the eccentricity can be a decimal number. And notice in this case, visually it looks like this distance is smaller than this distance. So it looks like PF, or what they call R, the radius here, is smaller than P to D. What that actually means is, I believe in this one, that means it would be an ellipse that one would be. And if they were equal to each other, that means E would be equal to 1, that would be a parabola. And if this distance was larger than this distance, then that would be a hyperbola. And that's one of the ways that you can tell. So what I'm going to do is just write down this, that eccentricity is PF divided by PD. That's equal to E. And we get it from, let's do a little quick one. I do that, and I do the focus point. Oh, I don't want to do that, Mike. I want to do a point to here. This is the whole thing is the directrix, but we'll call whichever point that we get to, we'll call D. So PF over PD equals the E. Now, if the E is equal to 1, that's a parabola. Parabola. And if E is less than 1, like this is showing, that would be an ellipse. And if E is greater than 1, that's a hyperbola. So there's some information to help you out. And that's one way that you determine it. One of the best ways you determine it. Now I could do some more drawing of those, but you know, you get that idea. If I had a one, let's do out like this. So if my focus point is here and my directrix is here, D, P, and F. Now you can see that P to F is much larger than P to D, so we're going to get a number where this is larger than that. That means that it would be greater than 1, so this would be a hyperbola. Okay? So one of the things you can tell is the shape of the arc, which you define by this, helps you determine an ellipse, or if it's just the right shape, it sort of breaks out of the ellipse mold, and that would be a parabola. And if it's even farther, then you're going to have the two of them. Okay, anyway, enough idea on that. I had drawn up some nice little graphic pictures of it, but I think that's about the extent of my artistic ability today. I think I'll hold off on that. Now, the next thing we need to do is the equation where you can determine where E is. You could graph and you can find that, but you usually can't easily. Instead, conics that are in polar coordinates have a particular equation that you look at. Okay. So the equation we use is R equals EP over 1 plus or minus, depending upon what it is, e times the sine of theta or the cosine of theta. We'll always be working with that type. But there's all these variations, because it'd be 1 plus e sine theta, or 1 minus e sine theta, 1 plus cosine theta, 1 minus cosine theta. And all of those, the book keeps referring to this, so hopefully you are already comfortable with this page. If not, get comfortable with it, because it really helps to recognize what those mean. So when you have cosine, notice these top two are cosine, and for the cosine ones, you are going out one way or the other. Whether it's hyperbola, ellipse, parabola, you are going where, I guess you say the direct ellipse is going to be parallel to the y-axis. Or you could say it's going along here, it's cutting into the x-axis. One way or the other. It's opening left and right. If you have sine in the denominator, that means you're opening up or you're opening down. Okay? So remember, memorize that. If you use an index card, make some notes to yourself about the differences so that you can see that. Okay, and now what we have, if it's plus, then we're opening that way. Or if the directrix is on the outside towards the positive. Or if it's minus, the directrix is towards the negative, or it's opening to the right side. Any way you want to remember it, but that's the kind of thing that you'll have to be able to do, or to use for these. And this works for all of them, because if this one were a parabola, it looks like this. If it were an ellipse, it's like this, but it's just going out farther. It would be going like that for an ellipse. And if it were a hyperbola, you'd have this one, and then there'd be a matching one over here. But you start off by making one of them. And that's why you use that to help define where you're at. So all of them have this basic thing. The amount of E will help us to determine what the which one that it is. So first I'll say a reminder: see page 900. It's a nice round number for them to put that on. Okay. But one of the other things to notice is that you have to have a 1 here. So let's take one of the equations and let's determine what it is. R equals 8 over 4 plus 8 cosine theta. Okay. Problem we have right now is that that's not a 1. So you've seen this already in a number of places in this section. You have to make that a 1, so the first thing you have to do is divide by 4 here, which means you have to divide this by 4 and that by 4. Everything divided by 4. What you're really doing is you're dividing by 1/4 over 1/4. So you're dividing by the number 1, you just make it something that helps you. In this case, you have to divide by 1/4 over 1/4, and so you get R is equal to 2 over 1 plus 2 cosine theta. This one we can work with, this one we can't. So that's your first thing to do. So if you were to get a question like this, and it asked you what the eccentricity is, you would have to change it to this first. Now you can see, what is it, the, okay, and then a different one. Oh, okay. I get 2, yep, I get that. So here, what I get, this is different from what I had thought for some reason. I don't know what. Oh, I know what. Now I put a 2 here. Oh, I was looking at the wrong problem. So what I'd like to do for a minute is, in order just to keep what I'm doing, please make this a 4. If you make that a 4, then that means this becomes a 1, and that's what I want. What I want is I want E is equal to 1. That's because I want to do this first one as a parabola, and I can't do it with a 2 there because that's a hyperbola. So E is equal to 1, which means it's a parabola. Okay, so that's a 4. When I divide them all by 4s, I should get a 1 here and a 1 there, and that means my E is equal to 1. So I know that that is a parabola. I know that because it's cosine, it's going to be opening one way or the other, and because it's positive, it's going to be opening this way. Let's see. Nope. Oh. Positive cosine opening that way, so the directrix will be there. So I know that when I do graph it, I'll be doing something like this. Give or take something like that. It'll be going that way. And I'll graph it in a couple minutes. The thing is, though, in order to graph it, I'm going to be using 0, 0 as the focus point, but I don't know how far to go to get to where this is, or how far to go to get to the directrix. That's what P is. So remember back up here, the P, that is the distance from the focus point to the vertex of any one of these things, to whichever vertex it is, whichever type of thing. That's the distance from the focus to the vertex, or from the vertex to the directrix. So we need that P amount in order to graph it. EP is the number on top when we have a 1 here. We now have a 1 here, so EP is equal to 2. We know that E is 1. 1 times P is equal to 2, so P is equal to 2 units. So with that information, knowing that it's going to be opening that way, and knowing that P is 2, we can now do an approximate graph of it. So for that, we're going to need a polar graph. Go ahead and grab one of the ones I gave you, please. And now I ran out of them, so I'll leave my own. So I'm going to do this one as R equals 2 over 1 plus cosine theta. E equals 1, P equals 2. So I'm going to come over here, and I'm going to look at the fact that if this here is the center, in fact, that's one of the little things that helps with this. All of these are always graphed where the focus point is going to be at the origin at 0, 0. All of them. So you always start there, that helps a lot. And P is 2. So that means if I come out to 2 here, here's my starting point. If I come out to 2 here, this would be, even though it's a polar one, we're going to draw this in order to know that we're going to have everything on this side. Okay? So now what we would need to determine is where are the rest of the points here? Where else are we going to go? I know it's going to open this way, but is it going to go this way? Or is it going to go way out wide here? So for that, what we can do is pick a few points. This one, for instance, this one was 0. This is 0 on the unit circle. And the cosine of 0 is 0, so that's why it's 0. 2 over 1 is 2. That's why it's a distance of 2. Let's pick 90 degrees. In fact, what I'm going to do here is I'm going to say that if theta is a certain amount, and if r is a certain amount, well, let's do a few. At 0 degrees, we know we're at 2. I'm going to do pi over 4, and then pi over 2, and then I'll come all the way over here to pi. Now, I'm not going to do pi over 4 yet because I want to show you something. Let's do pi over 2. The cosine of theta at pi over 2, oh, wait a second, something's wrong here, isn't it? Cosine of theta is 1 over here. Why am I thinking? Oops. Hold on, I think I made a mistake on something, didn't I? Let me get my mind straight around it. Because I was jumping to the sine of theta is 0. So this should have been 1. So when we're at 0, we're at 1. Something's off in my, P is 2. Let's put this one aside. Let me use a different example until I figure out what went wrong with that one. Hold on there. Cosine of theta, 1 and 2. P was 2. No, P is 1. No, P is 2. I specifically came up with P is 2. Hold on a second. P is that distance and that distance. So I'm wondering if I have something off on P there. I don't think so. I'll graph it. Because that's weird. That's off by 1, and I can't figure out why I'm off by 1. So give me a second to figure out why, and then I will pick up either that example or a different one. P is 4. So I mark it down 1 and 2. Okay. Okay, I see what my problem is. When I said P is 2, what I need to point out here, or what I need to do, is that that's the total distance from the focus to the directrix, not the focus to the point and then the point to the directrix. So let me start this one over. So let's do r equals 2 over 1 plus cosine theta, and e is 1 and p is 2. What that means, though, is that from the focus point 2 away, that's where the directrix would be, not all the way out at 4. So my vertex would be in the middle of that. Okay? And the way I'm going to determine that, theta and r. So I'm going to go back to still using 0, pi over 4, pi over 2, and pi. And at 0, because the cosine of theta is 1, or cosine of 0 is 1, I have 2 over 2, and that means we're at 1. So at 0, we have to go out to a distance of 1. And that's where we're going to start making our parabola. So the lesson here on this is to be careful about the fact that P is from the focus to the directrix, and in the middle of it will be the vertex. So that's what 2 is, not from the focus to the vertex, and that's what I was accidentally applying incorrectly. Now that you know that, you'll do it this way also, where you go focus all the way to the directrix. Now let's look at pi over 4. Well, no, I want to skip to pi over 2, because for pi over 2 going up this way, pi over 2, the cosine is indeed 0 there, which means that we're going to have 2 over 1, so we get 2. We're going from here to there. When I go to pi, the cosine of 0 is a negative 1. So if I make that negative 1, I have 1 minus 1, and I have 0, and I get 2 over 0. But 2 over 0 is not possible. Undefined. Now, if you think about it, undefined makes sense, because the parabola is going to go this way, and it's going to go this way, and it never turns in on itself, and it never gets to this line where it's pi. So it actually makes complete sense that a parabola should have the inside part of it be undefined, because this curve, which I now see is going to go that way, is never going to curve in this way like an ellipse does. An ellipse comes in that way and hits that. A hyperbola would have a line, wouldn't be undefined, because it would go the other way to the other part of the hyperbola. So you'd end up with a negative going that other way. So let's come back over to here. So I see this one. If I go, I don't even think I need pi over 4, because if I go from here to this one, I know pi over 4 is going to be in here. Instead, let's take something like this one, which would be pi over 3, 2 pi over 3. And the cosine at 2 pi over 3 for the unit circle is 1/2. Now I'm getting myself mixed up, and let's be careful, and let's use a unit circle. So at unit for 2 pi over 3, the cosine is a negative 1/2. Okay? So that means I would do 2 over 1 minus, or plus negative 1/2 minus 1/2. So that's going to be a positive 1/2, and I'm going to multiply by 2 on top and bottom, so that's going to be equal to 4. So I get a 4 here. So for this one, 1, 2, 3, and 4. I think that would be a pretty good start for the parabola. Yes?
I'm just wondering if we'll have a unit circle on the test.
Yes. Yes, you will. Now over here, because you have symmetry with it, you can go right over here to 270 and put that one. And you can come over here with the, let's see, that's at this spot. You can come over here to that one and do the same thing. Because you know that for a parabola, that, and I guess I should be curving that in a little bit more. It still is pretty reasonable. I've plotted enough points to know approximately which way that curve is going to go, and I only have to do it for one side because it has symmetry there. Take advantage of that symmetry. Okay, so let's go back over this, and especially since I don't want you to make the error that I started making there before. Okay, which one do I have it right now? There we go. Okay. So, Using this equation where it was 8 over 4 plus 4 cosine theta, I wanted to keep it for a parabola, that changes to 1 plus cosine theta, and that gives us an eccentricity of 1, tells us it's a parabola, gives us a p of 2. Over here, that meant I knew the directrix would come to here, and I really didn't even have to have that because once I start doing a table of values, I only need just enough points, which was this one, and this one, but this one was worth doing too. Just enough points to see which way it was going to graph, and then use symmetry for the other part. Okay. Let's see if I'm going to do, okay, let's pull up another one. And you have room on this one or on the back if you want to do it, because this will be the second one. The last one that we'll do here will be this one, or the last example like this. So, I'm going to give you, this is still part of, what, 9-6? I'm going to give you r equals 8 over 4 plus 2 cosine theta. Oh. No, let's make that minus, because the last one, so cosine or do I want to do sine? I think I want to change the sign. We just did a cosine one, so let's do it differently. I have a couple of problems here I'm looking at, and I think I'm going to make it so it's 8 over 4 minus 2 sine theta. Let's do that one this time. So you're going to get to do it with sine, and you're going to do it with a different e on here. Okay, so I'm going to ask you right now to, 1, change it so that you get a 1 there. Then 2, find what the e is equal to. And then 3, find what the p is equal to. And then 4, graph it. And I recommend you do that. And I will do a few of the things with you, but I'll do it after you, so I want you to get a chance to do each one of these. Okay, so first change it around so you get a 1 in there. Divide and multiply by. You should be past this already, but you should have this equation. So you should have a 1/2 here. That's the part that can be confusing unless you're just really careful with your numbers. If you got to this, now you can determine the rest of it. And I will remind you that e is always positive. The negative here isn't used for the e, it's used for the sign to tell you which direction the up and down. And with that, you should have determined that the e is 1/2, which, by the way, does tell you, because it's less than 1, you're dealing with an ellipse. And that your p is 4. So if you weren't sure about that, this is how I determined about the p is 4. And now work on a table of values so you can graph it and do that on your other paper. see that you're on the right track. Here is what I'm coming up with so far. Using that, and with the sign when theta is 0, when it's pi over 2, and I'm working on pi now. So that would be 2. Should be able to get 4 over 3 for this last one. If you don't, think about what you did and look at the steps that I have here. First putting in the -1, and that's 1/2. That means 2 over 3 halves, which divide that, and you get that. So that means I'm at just past 1. Show it again, I can't draw very well. Now, this would have been a good one where maybe if I did the 60 degrees and 120 degrees, that might have been good to get those points in better. Well, I'm not too sure it would have made my drawing in better, because that's not going to help me necessarily. But I had these 4 points, and I knew it was supposed to be an ellipse, so this showed me it was going to go that way. So if you got to approximately that shape and you were able to get these numbers in there, then you can graph these. So what you're going to want to do for me, I'm going to be asking on the test for you to determine eccentricity. And no, I'm not going to give it to you in this form. You're going to have divide or to get it in this form. So I'm going to ask you eccentricity. I'm going to ask you to determine what type of conic it is if I give you a different one, maybe the same one, but maybe a different one. And I'm going to ask you how you know. So that means you'll have to tell me that it's because E equals 1 or E is less than or E is greater than. So you actually have to say that. And then I'm going to make you graph one too. Okay. So I will give you one of these where you have to graph it, and I may or may not make them the same one. I might make them different, but I haven't gotten that far on the test yet. Okay, that's polar coordinate graphic. A new one, but I have realized that on various things you see in other tests, recognizing what eccentricity is, recognizing how to find it from an equation, which is really just so simple as finding it from the bottom part here, and what it means, which type of conic it is, those ones are pretty important. Now, I like to do the graphing. You're stuck. You have to do some graphing for me. But if you think about the various standardized tests and stuff you do, you usually don't have to do much graphing. What you do have to do is recognize stuff. So really my focus for you here will be to recognize the eccentricity and the equation and how to change it and recognize what the eccentricity means. But I'm still going to make you graph one.